Okay, let's get into this. So much of our world really hinges on measurement, doesn't it?
Oh, absolutely. Daily decisions, big scientific leaps, it's everywhere.
Right, from just like scrolling reviews online to, major lab breakthroughs. We're always scoring things, ranking them.
Quantifying everything.
Exactly. But how often do we actually stop and think about the concepts behind those numbers, the tools themselves?
Not often enough, probably.
So that's what we're doing today, a deep dive into these foundational measurement concepts. We've gone through a whole stack of research, articles, notes.
Some really insightful stuff.
Yeah, trying to pull up the key nuggets for you. The goal is really to give you a shortcut, sort of, to understanding how we quantify the world.
Like becoming a more informed data detective.
I like that, a data detective.
And it's not just going to be, dry definitions. We found some genuinely surprising history in there.
Oh, definitely.
And we'll connect the technical bits to, well, how it actually plays out.
Yeah.
Because understanding how something's measured, that's just as crucial as the number itself, really.
It really shapes how we see things.
Completely.
And speaking of shaping things, maybe we should start with that sobering piece of history from the sources.
Yeah, probably best to address it head on. It's pretty stark.
It talks about the nefarious use of assessments. It's a really powerful reminder that these tools, even seemingly objective ones, well, they can be misused badly.
Yeah, the source material is very direct about this. It gives this specific historical example of IQ tests used to support eugenics.
Right.
And it even includes that chilling phrase associated with them. Low IQ should not breed.
Wow.
Yeah, it's a direct point from the sources showing how measurement was actually weaponized. It underlines the power these tools have and, the responsibility that comes with using them.
It absolutely does.
And the sources make another critical point here. This isn't just ancient history, sadly. No, they state, quote, "We still see assessments that bias based on demographics, even today."
So understanding this history is vital for critical thinking now.
Absolutely vital. It forces you to question the data, doesn't it? It shows why understanding the principles and the potential harms is just so important.
Okay, so that context, while definitely unsettling, it really does highlight why getting measurement right matters so much, applying the principles correctly, ethically.
It sets the stage for why we need to understand the foundations.
Exactly. So let's pivot from that history to the building blocks themselves, the types of data we actually work with.
Makes sense.
Our sources lay out 4 fundamental types of variables. Think of these as like the basic categories for any data you might encounter.
Yeah, knowing these is absolutely foundational. Get them wrong, and your analysis can go completely sideways.
Okay, so what's the first one?
First up, we've got nominal variables. These are essentially just categories, names, labels, but with no inherent order or ranking. The example given is colors of cars. Red, blue, green. They're just different. One isn't higher or more than another.
You can count how many blue cars, but you can't average blue and red.
Exactly. No mathematical averaging makes sense there.
Okay, what's next?
Next is ordinal. Now here, the data can be ranked. There's a clear order.
Okay, so like first, second, third.
Kind of. The sources give TV ratings like excellent, good, fair. Excellent is better than good, but the difference between excellent, good might not be the same as between good and fair.
The steps aren't necessarily equal.
Precisely. Class rank is another example they use. Rank 1 is definitely ahead of rank 2, but the performance gap might be huge, while the gap between rank 20 and 21 could be tiny.
Gotcha. So order, but not equal intervals.
You got it. Then we move to interval data. Now, here the data is ordered, and the differences between points are meaningful and consistent. Equal intervals.
Okay, like temperature.
Exactly. Temperature in Fahrenheit is a classic example from the sources.
Yeah.
The difference between 10 and 20 degrees is the same as between 70 and 80 degrees. It's 10 degrees.
Makes sense.
But here's the twist. There's no true inherent 0 point. 0 degrees Fahrenheit doesn't mean no temperature.
Right. It's just another point on the scale, not an absence of heat.
Exactly. Year of birth is another example. You can measure the interval between years, but year 0 doesn't mean no time. So you can add and subtract interval data, but multiplication and division get tricky. You can't really say 40 degrees F is twice as hot as 20 degrees F.
Okay, that's a key distinction. So what's the last type?
The last one, and in many ways the most informative, is ratio data.
Ratio, okay.
This has everything interval data has order, equal intervals, plus it has that true inherent 0 point. 0 actually means the absence of the thing being measured.
Ah, so like height Zero height means no height.
Perfect example. Height, weight, age. These are the illustrations from our sources. 0 weight is no weight. Because of this true zero, you can do all the math, add, subtract, multiply, divide. You can say someone is twice as tall or half the age.
And that's why distinguishing these is so important, because the math you can do depends on the type.
Absolutely. If you treat, say, ordinal TV ratings like good or fair as if they were ratio data and start calculating averages, you might get a number like 3.5 stars, but it doesn't really mean anything mathematically precise because the intervals aren't equal.
That really clears things up. Okay, so we know the types of data. Now, how do we know if the measurements we're getting are any good? How do we trust them?
Ah, yes, the quality control question.
Our sources really focus on this, introducing reliability and validity. These sound crucial.
They are absolutely fundamental. This is how we judge the quality of a measurement tool or process.
So let's start with reliability. What's that about?
Reliability is basically about consistency, dependability. If you measure the same thing again and again, do you get roughly the same result?
Like stepping on your bathroom scale multiple times in a row?
Exactly. If it gives you wildly different readings each time, it's unreliable. The sources mention specific types, like test, retest reliability.
Which is?
Just what it sounds like. Give a test today, give the same test next week. Are the scores consistent?
Okay, makes sense.
Then there's internal consistency. This looks within a single test or survey. Do all the different questions or parts seem to be measuring the same underlying thing?
So if you have a quiz about, say, history, are all the questions actually about history, or did one about chemistry sneak in?
Sort of, yeah. Or in a satisfaction survey, are all items really tapping into satisfaction? It checks if the instrument is measuring consistently within itself.
Okay. What about this coefficient of determination, CE?
Right, the CE. This one's really useful. It basically tells you how much of the variation in one variable can be predicted or explained by the variation in another variable.
So if two things are supposed to be related.
Yeah. If someone claims, say, studying time strongly predicts test scores, the SEAC would give you a percentage. A high SAD, maybe 80%, means studying time explains a lot of the score differences. A low SAC means, well, maybe studying time isn't as direct a predictor as claimed.
So it measures the strength of the shared relationship.
In a way, yeah. How much variance they share. It's a check against finding connections that aren't really that strong.
And standard error of measurement, SEAC.
CM. Okay, this one tells you about the inherent wobble or imprecision in any individual score. No measurement is perfectly precise, right?
True.
So the CHAC gives you a range. If a test's a CM is, say, 3 points and you score 85, your true score is probably somewhere between 82 and 88.
It's like an expected margin of error for any single score.
Exactly. It quantifies the measurement's precision, like that dart player analogy. Even a good player has a spread around the bullseye. SEM describes that typical spread for a measurement.
Okay, so reliability is all about consistency and precision. What about validity?
Right. Validity. This asks a different, maybe even more fundamental question. Is the measurement actually measuring what it's supposed to measure?
Accuracy, essentially.
Accuracy is a good way to think about it. Remember the scale example. It might be super reliable, giving you the same weight every time.
But if I'm holding weights, it's not a valid measure of my weight.
Exactly. Reliable, but not valid for measuring your body weight alone. The sources also mention factor analysis here in relation to validity.
Factor analysis? What's that?
It's a statistical technique, kind of like a detective tool. If you have lots of different measurements or survey questions, factor analysis tries to see if they cluster together, if they're actually measuring a smaller number of underlying factors or concepts.
So, like, if you ask 20 questions about job satisfaction, it checks if they really boil down to maybe pay satisfaction and work environment satisfaction.
Precisely. It helps see if the structure of your measurement aligns with the concept you think you're measuring. It's a way to gather evidence for validity.
Okay, so we need both reliability, consistency, and validity, accuracy. What's the link? Can you have one without the other?
Great question. And the relationship is key. You can have reliability without validity.
The broken scale example.
Perfect.
Yeah.
Consistently wrong. But you cannot have validity without reliability.
Why not?
Well, if your measurement is jumping all over the place, unpredictably unreliable, how can it possibly be accurately hitting the true value? Valid. You need consistency first before you can even assess if you're consistently measuring the right thing.
So reliability is necessary, but not sufficient for validity.
You've got it. They're deeply connected.
Okay, Beyond these big two, reliability and validity, the sources also mention a few other related statistical ideas.
Yeah, concepts that sort of fill out the picture.
Things like the normal curve, that bell shape you see everywhere.
Right. Describes the distribution of many natural phenomena.
And standard deviation, which tells you about the spread or variability in your data.
How clustered or spread out the scores are.
And correlation, showing how two things move together, often shown in a correlation chart.
Yeah, visualizing those relationships. These all help us interpret the measurements we get.
And then there was probability and something called sensitivity and specificity. These sounded quite practical.
Oh, extremely practical. They come up constantly, especially in things like medical tests or even like spam filters.
Okay, explain those. Sensitivity.
Sensitivity is about correctly identifying the positives. You have a test for a disease. Sensitivity is its ability to correctly spot everyone who actually has the disease. A highly sensitive test catches most cases.
The true positive rate.
Exactly. And specificity is the flip side. It's about correctly identifying the negatives.
So correctly identifying people who don't have the disease.
Precisely. The true negative rate. A highly specific test correctly clears most healthy people.
And there's often a trade-off, right?
Almost always. Making a test super sensitive might mean it flags some healthy people by mistake, false positives. Making it super specific might mean it misses some actual cases, false negatives. Understanding sensitivity and specificity helps you evaluate how well a test or classification system works in the real world, considering those trade-offs.
That's really useful. Okay. So quite a journey we've taken here.
We have, from that difficult history.
Yeah, the reminder of potential misuse.
Through the basic types of data, nominal, ordinal, interval ratio, which you really need to get right.
To the absolute cornerstones of good measurement. Reliability meaning consistency.
And validity meaning, are you actually measuring the right thing? Plus those related concepts like sensitivity, specificity.
It really feels like understanding these gives you, the listener, a kind of X-ray vision for data.
It does. It helps you look beyond just the surface number and ask critical questions. Is this consistent? Is it measuring what they claim? Is there bias? Because numbers without that context, well, they can be used to tell any story, can't they?
Absolutely. So this deep dive hopefully gives you that shortcut to understanding the skeleton, the backbone of so much information you see every single day. It helps you be genuinely well-informed.
Not just knowing what was measured, but how and how well. That's the key difference.
Yeah.
So maybe the final thought to leave you with, circling back to that history.
Yeah.
Given the power we've seen measurement holds and its potential for misuse, like with those IQ tests, how does really grasping these concepts change how you look at data now? How do you question it? How do you interpret claims backed by numbers? And maybe, what responsibility do we all have, do you think, to become more literate in these tools that fundamentally shape how we understand our world?